clarification and treatment and system requirements analysis. This work is an extension and it actually complements the paper I gave you last week, and going into addressing one of the major questions that came up as a result of last week's discussion. My objectives for you this session is that I would like you to be able to identify functional failures, 4 different types of subsystems and interfaces that you're analyzing, to be able to determine behavioral consequences of those failures for different kinds of system requirements, and to be able to capture the results in your system requirements analysis. The topics I'll be going through, the objective we just discussed, get into a little bit of the motivation, discuss the sufficiency of interface analysis for this task, discuss interface anomalies, the behavioral consequences, what the benefit and effects of performing the functional failure analysis are. I'll discuss a little bit how we're applying this and conclusions. If you have clarification questions that you don't understand something I'm saying, please ask. If you have a discussion question, please hold that toward the end. I want to start with some definitions so you understand the terms I'm using. Anomaly, that's the same term we used last week, departure from the normal form, order, or rule. In this paper, I'm using functional failure to mean any failure, any anomaly in a subsystem boundary, whether it's having to do with anomalous functions or anomalous environments or any other design constraint that is outside of its normal condition. Our motivation is that failure to treat anomalies may lead to either indeterminate or incorrect system behavior. Indeterminate meaning we didn't specify how it was supposed to operate, and therefore any range of operations is possible, and we can't even predict what might happen. Incorrect behavior means that the system or the detailed design is incorrect. And again, I assert that a good SRA and the design should evidence neither incompleteness nor incorrectness. Now last week, and in fact every one of the 5 times I gave last week's paper, we've had the same question, which is how does one identify the specific anomalies? The first 3 times I gave the paper, the answer was I don't know. The last 2 times I said wait for the next paper. And just in comparison, last week's paper, which was written for a 1995 conference, we identified the necessary conditions for completeness. The 1996 paper being presented this summer, and you're getting the first presentation, identifies sufficient conditions for completeness. And that's what we'll be talking about today. To summarize last week's paper, we developed a set theory model that basically said if I can define all possible conditions and write a behavior for each of those conditions, I've completely defined the system behavior. First in terms of a set of antecedents A and its complement, or in terms of a set of conditions A and other sets of conditions whose union is the complement, not A. And we asserted that no functional requirement with an antecedent A could be considered complete unless there also exists one or more functional requirements whose union is the antecedent not A, the set of all possible antecedents. And the key question, we got it again last week when we were talking, how does one identify B, C, or figure out how many of those you actually need? And that's what we're going to talk about today. The key to figuring that out is looking at the interfaces of the subsystem you're analyzing. Everything you need to worry about is on the interface boundary. That's simply because the scope of the system requirements analysis is at the interface of the subsystem you're analyzing. You don't need to know what's going on inside, because that's where we perform the detailed design, the how I get to the interface condition. But when we look at the system requirements analysis, and the scope of that being what happens at the boundary of the subsystem, no matter what it is, there exists no anomalies that are within the scope of the system requirements analysis, and therefore needing to be documented at this level of the design analysis, which fail to be manifested at the subsystem boundary. And you can pick anything you want, whether it's communications, like for the avionics we're building, we have these kinds of functions, digital discretes, analog discretes, power, and so forth. Or in more general condition, we're building mechanical systems with pistons and rods and so forth. Or we have cooling fluids or functional fluids for example, a chemical process. Or we have a human interface that we need to interact with for display of information or for receiving inputs. In each case, these things are manifested at the boundary of the subsystem we're analyzing, and that's what we need to be looking at in terms of anomalous behavior. And so, given the definition of what it is we're trying to accomplish in the system requirements analysis, and that is specify the behavior at the subsystem boundary, it's apparent that analysis of the interface conditions over all parameter space associated with that item is sufficient to establish the completeness of the analysis of the anomalies, and in fact, it's sufficient to establish the completeness of the system requirements analysis. In other words, if I analyze every one of my interface parameters over its complete range that is possible, some of those will be the kinds of things that I would normally analyze. For example, in data communications, when you receive a certain message, go do a certain function. That would be part of the parameter space for that interface. But there's lots of other things that can happen on that interface. And if I analyze all the parameters on that interface, I will have been able to derive all of the conditions that the subsystem can experience associated with that interface. And included in that will be anomalous conditions. And when I analyze the interface conditions over all parameter space, I assert that we will have a sufficient condition for the completeness of the system requirements analysis. And so the rest of what we'll be talking about is what are the interface anomalies for different kinds of interfaces. If we look at functions, in other words, items passing across the subsystem boundary that we want to, in order to be able to perform, have the subsystem perform functions, we typically have inputs, which are the conditions that the subsystem experiences, and the subsystem itself basically is a transfer function, converts inputs into outputs. When you experience a certain condition, you provide a certain output. And you can write this for any kind of a subsystem you care to. You can basically make three categories for the inputs. First, an out-of-range input means it's a not valid condition whenever it's experienced is an anomalous condition. And notice we've broken out time explicitly in this description as a parameter. And it's a more general variable as far as interface parameters, but we've broken it out explicitly just because I think it provides benefit. You can have valid or in-range inputs that occur at the wrong time. You're in the wrong state, you're in the wrong mode, you're not supposed to be receiving that input, but you need to describe what the system should do if it gets that input at the wrong time. And I have seen that implemented where certain subsystems executed a function that was correct if they'd been in the correct mode or state, but because they were not in that mode or state, the behavior that was executed was incorrect. There's a third type of input, which is one that's incorrect, meaning it's the wrong state, but it's an in-range input, but you don't know, the receiving subsystem can't tell that it's an incorrect input. In other words, anytime an in-range variable is received at the right time, it has to be accepted as truth by the subsystem receiving it, unless there's some means for independently checking a redundant input, for example, where it can compare and say, well, these don't agree. And then, of course, our analysis has to say what to do if the inputs don't agree. So I have this listed explicitly, but you can generally not analyze this because, as far as the subsystem is concerned, it's a good input. Outputs, 3 types. First one is it's out of range. Second, it's an in-range output, but it's in the wrong motor state. And third, it's in range, but it's the wrong value. So I call it incorrect. It has the wrong value. There's a couple other things that can happen with our subsystems where if we zoom out a little bit from the particular box we're looking at, we may figure out that, by golly, because of the way the system is interconnected, an interface anomaly at one interface can actually affect multiple subsystems. Typically, that's manifested as an impedance problem, and there are extensions to radiation and fluids and so forth that relate to impedance problems. Either too much, it's an open circuit, or too little. And I've shown an example of a short circuit here, where the short circuit on this guy's input is at the same time manifested as a problem over here because they share an input. So when we do our system requirements analysis for these conditions, I need to understand that these two subsystems are experiencing the same input condition. This categorization came out of a couple of other papers, one by Steve Spangler several years ago, and Steve is in Cabin Management System. His work was extended in last year's INCOSE conference by James Armstrong, and he talked about a lot of different ways for functions to fail. And I've regrouped them and organized them in a different way that I think simplifies them and captures the essence. Whether it's in range, whether it's valid, meaning it's in range but at the wrong time, or whether it's just an out of range variable. Environments are really interesting because most of the time we don't want to measure them, but we still want to know if the system's going to respond correctly. Normally, the way we should write a requirement having to do with environments is, while the environments are in their valid ranges according to the section of the requirements document that describes all of the environments for that subsystem. However, when they go out of range, we generally have two choices. Either we don't really care to detect the specific environment because we're not going to do something based on the value of the environment, but we want to make sure that our system behaves correctly under all conditions. So we write the requirement in terms of the output as such. While environments are not in valid ranges, in other words, the environment is outside the range we designed the system for. We don't expect it to necessarily operate correctly, but it actually may. While they're not in valid ranges, but the subsystem is able to maintain output for its requirement. In other words, if you can operate, do so. If you can operate correctly based on all the other conditions you're experiencing, don't worry about it. For example, we design a system to operate up to 70 degrees C. Okay, and that's tested and checked and everything works fine. Well, if the environment is now 71 degrees, we generally don't want to cease operation. What we want to make sure is it doesn't go into incorrect operation. So as long as the output or outputs are satisfying their operating constraint, then there's no reason not to keep operating. But if the environments go out of range, are not in valid ranges, and the subsystem is unable to maintain the outputs for the requirement, then what do you want it to do? What do you want it to do? We don't want it to operate incorrectly. We could ask it to operate in a degraded manner, provide half the power you normally do, provide half the regulation. We talked about a little about this in the example for the power distribution unit last week. Or we may just say shut down. Well, the key thing here is you have to be monitoring your output or your outputs to know whether you're operating correctly. There are conditions where the environment, actually, you want to measure the environment in order to be able to shut down prior to doing something bad on your output. While humidity, for example, if we look at humidity, is not in valid ranges, inhibit all outputs. And the work we were doing on cabin management system, we saw a function called a humidity detector in the videotape players for the airborne entertainment equipment, because they don't want to operate videotape players in a high humidity environment because the tape tends to get wrapped around the head. So they added an environmental detector so that they could shut down the tape player. So they had to detect the humidity. So in this case, detection is required because we want a unique behavior defined. So here's three different ways to treat, or here's two different ways to treat the detection and response to anomalous environments. Most of the time, these are going to be so whats. But in case we get a condition where the system may not operate in a nice manner, we want to be able to establish that we have prescribed what the output should be. Either operate correctly or don't operate at all, or operate in a degraded manner. But it's no longer an arbitrary behavior based on fact just because the environments went out of range. Physical interfaces, stuff at boundaries. We have basically two different types. One is when they have functional attributes, we should analyze them as functional interface anomalies. You can think of, well, I've got a wire harness that connects up to my plug. Well, what if that becomes disconnected? Well, I'm going to see that disconnection in the fact that I'm no longer receiving inputs, or I have excessive impedance on outputs of anything that goes through that connector. If we're dealing with mass transfer, like chemicals for a feedstock process, if we're dealing with, well, I've got cooling water down here, other kinds of things like that, mass transfer, I want to know what happens if I'm no longer receiving the feedstock. And it's especially true when you're combining chemicals and all of a sudden one goes away. Have you analyzed the behavior of the system when you've got 2 out of the 3 inputs to the chemical process? Mechanical implementation, for example, a piston that's providing work, providing force. What happens on that? Well, it's really a function to provide motive power. And radiation is either an input, in other words, you have a process that's depending on radiation as an input to perform a function, or the subsystem is a source of radiation for some other system, in which case we're dealing with the fact that it's a function. So you get back to the items that I listed before, which are, is it the correct value, is it the correct timing, is the value correct for the state or mode you're currently operating in. If you have other physical interfaces not associated with functions, then you're back to the question that we asked for environmental constraints, which is, do I need to detect it? Or do I just need to monitor the output and make sure I don't do something wrong, I don't operate incorrectly? For example, a loss of cooling water is similar to getting in an over-temperature condition. I don't want to operate incorrectly at the point where I can no longer operate correctly. I would like to shut down. Or a loss of radiation protection. Well, that's kind of like having insufficient impedance of the radiation environment. Or physical attachments and structural integrity. If things are not holding together, can I sense when I no longer have a subsystem that's operating? Again, what I'm trying to avoid is operating incorrectly, being able to sense that I'm operating incorrectly and doing something about it, rather than just having the subsystem operate any old manner in which it chooses. So once you've identified the interface parameters, then you have to analyze them into what are either valid ranges or invalid ranges. And in this illustration, I have a parameter P1, it's a generic parameter, and it's got 2 valid ranges and 3 invalid ranges. Now I need to define a behavior for each one of those, and let's assume this is this range here is all of physically possible space. So if I go from here to here, I've covered all possible conditions for that parameter. Well, I've got 3 invalid ranges and 2 valid ranges, and I just want to make sure that I've defined a behavior. Now, it may be that the valid ranges both have the same behavior. While the parameter P1 is in this range or in this range, do the following. Or these may be 2 different states of a discrete. When it's in this range, consider it a 1 and do the following. When it's in this range, consider it a 0 and do the other thing. And in these invalid ranges, I may want the behavior to all be the same. Anytime it's an invalid range, do the following. Or this invalid range may have a behavior different from this other invalid range. But the fact is, you partition the parameter space completely. You completely covered it, and you go through these ranges one by one and write down what is the behavior I want under that condition. Once that's defined, you've covered that parameter. And you say, well, yeah, but what if you've got more than one parameter? And we almost always do. Time being the most obvious example of the second parameter, especially in avionics. Well, the range of validity for parameter P2 and parameter P1 is at the intersection where they're both valid. So out of 15 possible intersections, there's only 2 that are truly valid. Some are doubly invalid, some are singly invalid, these gray areas being singly valid or singly invalid. But you've got 2 choices. You can either define the behavior explicitly at each of the invalid points. In this case, we've got 13 invalid pairs of conditions. Or you can define a precedence and say, well, in the case of multiple invalidity, always perform the behavior associated with P1. In other words, it doesn't matter whether P2 is valid or invalid. If P1 is invalid, always do the behavior associated with that range of invalidity of P1. And again, the behavior associated with each of these points of invalidity can always be the same. Shut down. Whenever P1 or P2 is invalid, turn off. Shut down. Don't do anything. Or you may choose to have a separate behavior depending on the specific range of the parameter. In any case, when you look at the parameter space, again, evaluating these 2 parameters, we can say, well, if I have a behavior defined for each one of these conditions, I know that the union of all my antecedents is the universal set because I've covered each one of these parameters over its entire physical space. And this can be somewhat laborious as the number of parameters gets to be large. But remember, the behaviors associated with invalidity do not have to be unique. I mean, you can have the same behavior for each one of these points of invalidity. And now, a question that I was asked the very first time I gave last week's paper, which is, well, what about tolerances? And I think I had not thought about it enough to be able to come up with a good answer. And that's what I've been starting to think about some more. The reality is, especially in hardware systems, our line between valid and invalid may not be infinitesimal. Sometimes it can be as large as the range of validity. You say, well, what happens in here? Because it says the fact is the measurement is made by the subsystem that's performing the requirement, because that's the subsystem that has to decide whether it's a valid input or not a valid input. Well, software always has to come up with an answer. It's either a 1 or a 0. Or it's a 1, 2, 3, or 4, but it can never be fuzzy because the software has to make a conclusion. Hardware doesn't always have to make conclusions. It just says, here's my output. It's 3 volts plus or minus a half a volt. Well, if the downstream system receiving that is looking for 3.6 volts, may or may not interpret that previous system's output the same way it was intended, because the measurement, again, is always made by the subsystem performing the requirement. Well, even when we are faced with this problem, we can still define the behavior. And there's a couple ways to do that. One way that's commonly done is we use what's called hysteresis, where the required behavior is different based on the derivative of the parameter. In other words, if the parameter is increasing, the trip point for a change is on the upper end. And if the parameter is decreasing, the range of validity extends to the lower end of the possible range of validity. That closes the gaps quite a bit. It doesn't get rid of them completely. And in fact, what you often end up with is explicitly either of two behaviors is possible. And you say, well, how do you analyze that? Well, in the requirements, that's what you write. You say, if you can maintain the output, do so, and if you can't, shut down. Now, I've defined two possible behaviors, and you say, well, how am I going to predict what the system is going to do as these parameters move through this range of possibly valid states? And basically, you have to do it based on a prediction of the distribution of the parameter itself. And James Sanchez at Hughes wrote a paper based, looks like it's springboarded off the paper I wrote last year, and it's in the proceedings of the INCOSE for 1996, and I have a copy of that. And he basically takes the model and extends it into a probabilistic realm to deal with the kinds of things he's worried about in signal processing. But at a minimum, we've still defined the possible outputs. In other words, the output is not arbitrary. In this case, it's one of two states. It's either associated with being invalid in this area, or it's associated with being valid. I may not be able to always predict exactly what it's going to be because of the tolerancing, but I still have a definition in the system requirements about it's got to be either this one or this one, and it's not arbitrary. Now, once you've analyzed all your parameters, your top-level system requirements that are handed to you help you define what the behaviors are associated with those antecedents. Because you may have a requirement to operate through any single failure. That's not atypical. That may require redundancy. You may have a requirement to record and/or report failure or loss of function. Common built-in test kind of requirement. You may have a requirement to switch to a spare that's already there. That's another form of redundancy. You may have a requirement to reset. I don't like the situation, go back and start over. We often do that when we get in conditions we don't understand very well, or simply a requirement to limit damage. And I've used all of these. It depends on the top-level system requirements, whether you have operate through or built-in test reporting requirements, etc. The key here is that once you've defined the antecedents, then in the SRA you can explicitly link those input conditions to their consequences. Which of these am I going to choose? Well, it depends on the system requirements and the specific condition you're experiencing. But now I've already made up my table of possible input conditions, the input anomalies, and I should be able to map to prescribed system behaviors. Having done that during the system requirements analysis makes life a lot easier for everybody who has to use the results for the system analysis. For example, failure mode criticality, safety, and built-in test analyses, because now whenever a failure is experienced in the system, all I have to do is look it up in the SRA, system requirements analysis, and the behavior is defined. In other words, the person doing the failure analysis or built-in test coverage analysis doesn't have to postulate, gee, I wonder what the system's going to do in this case, because I don't see anything written in the system requirements about what it should do in this case. The advantage here is now we've documented all this stuff in the system requirements analysis, and it's available for everybody. The reliability people, the built-in test people, the safety people, and the certification people. Everybody gets a stab at it because it's now in this database. So, what's the effect? Well, The SRA is complete in terms of the antecedents. There are no parameters that the subsystem can experience that are not defined in the system requirements analysis. The antecedents provide coverage over a complete range. The union is the universal set. The antecedents have no intersection. That's really important. We talked about last week in terms of mutual exclusivity. And each antecedent has a prescriptive behavior, a shall, associated with it. Therefore, there exist no anomalies manifested at the subsystem boundary which are not captured in the SRA. And you can say, gee, under all conditions, I know what the system is going to do. And I'll caveat that a little bit with, because of tolerancing, it'll either do this or it'll do this. And I could run an analysis to say, based on my analysis of the design and the distribution of inputs, 90% of the time it'll do this and 10% of the time it'll do this. But that's the next area I want to work on, is that distribution idea. Now, how's this working? Have you tried it? Yes, I've tried it. Finding out whether my customers like it. Okay, we're using this on the phased array antenna program, and I didn't tell the people who were receiving requirements that this is what I was doing. I just kind of changed the way we were doing it. Our program phases, we're getting close to PDR. We probably have a PDR about now and satisfy all the things. I went through the requirements to see how much growth you actually experience. How many more shalls do you get by explicitly annotating them? And it looked like to me, based on my small sample, because it's a pretty small program, we had about 10% explicit growth in shalls. There was another 10% growth that I figured probably wouldn't have been there in Rev New or Rev A, but by the time you got to Rev C or D, they would have flowed in from the test program, because the test program would have come up with all kinds of conditions. So this isn't a very large growth. Most anomalous conditions were implemented as inhibit operation. We have a subsystem that's just for entertainment. If it doesn't work, fine. You know, things break, stuff happens, but it's not critical to the safety of the airplane. It typically does require that we monitor the output. That's the only way you know whether the subsystem's performing correctly. The key thing is it really does represent a paradigm shift for the people doing the system engineering work and the hardware design, because they're having to respond to such things as inhibit outputs. And you don't want to do that more often than is absolutely necessary. And so dealing with the tolerancing associated with those requirements decisions has been a bit of a learning point for us. Based on my small sample set, the technique is being well received by software, and I think there's a couple of reasons for that. It's very consistent with the normal constructs they use of if, else if, end if. Else, excuse me, we've got the else, that's the key one, that's the one that closes the set and makes sure you have universal coverage. But it also predefines all the conditions that they're going to have to design for anyway. In other words, it was typically software designers who were coming up with the what-if conditions that launched me into this discussion initially. And because of this discipline, it really forces a systems engineer to do a better job on the requirements. In other words, making sure that all the requirements satisfy the test of being a good requirement. It tells you what, how well, and under what conditions to perform a specific function. And so all this stuff, all this works together, we think, to provide a better requirements baseline, and we hope it's more stable, and that we'll see fewer changes rolling back up into the requirements as the design progresses. And I guess I'll let you know at CDR how we did. Conclusion. We've established sufficient conditions for the SRA by analyzing the functional failures of the subsystem interfaces. And that's the key to allowing this to be tractable, is I don't have to go inside the LRU. All I have to do is look at the subsystem boundary and say, is it manifested at the subsystem boundary? If it is, then it's in scope. If it's not, it's detailed design, and I don't really care about it. The technique complements the necessary conditions test, so now I have necessary and sufficient conditions for completeness of my SRA. That's a good position to be in if you're writing requirements. The result is deterministic or probabilistic system behavior in that there exists no what-if conditions that I haven't captured in the SRA, and now I can go verify them. I can go verify any parameter in any place in physical space and see that the system behavior is what it was supposed to be. The other nice thing about this is this can be done at any level of requirements or design analysis. We had a question last week about what if I have a system that has 100 states in it? Well, that's typically at the more detailed design level, but it's the same idea in that even at the design level, if I know my inputs, I know my outputs, I analyze those across all parameter space, and then I can define behavior associated with that. And whether that's a top-level requirement or a detailed design, I can use this technique for both. And we can also use the resulting system requirements analysis to support these other analyses, failure mode analysis, criticality analysis, built-in test, and safety. So, are there any questions that you have? We have a couple of minutes. If not, I thank you very much for attending.